Cumbre Vieja tsunami hazard. Cumbre Vieja tsunami hazard. The island of La Palma in the Canary Islands is at risk of undergoing a large landslide, which could cause a tsunami in the Atlantic Ocean. Volcanic islands and volcanoes on land frequently undergo large landslides collapses, which have been documented in Hawaii, for example. A recent example is Anak Krakatau, which collapsed to cause the 2018 Sunda Strait tsunami, claiming hundreds of lives. Stephen N. Ward and Simon Day in a 2001 research article proposed that a Holocene change in the eruptive activity of Cumbre Vieja volcano in a fracture on the volcano that formed during an eruption in 1949 may be the prelude to a giant collapse. They estimated that such a collapse could cause tsunamis across the entire North Atlantic and severely impact countries as far away as North America. Later research has debated whether the tsunami would still have a significant size far away from La Palma and whether the collapse is likely to take place in a single failure, with evidence indicating that most collapses in the Canary Islands took place as multi-stage events that are not as effective at creating tsunamis. Other volcanoes across the world are also at risk of causing such tsunamis. Sector collapses and tsunamis caused by them. Giant landslides and collapses of ocean island volcanoes were first described in 1964 in Hawaii and are now known to happen in almost every ocean basin. As volcanoes grow in size, they eventually become unstable and collapse, generating landslides and collapses such as the failure of Mount St. Helens in 1980 and many others. In the Hawaiian Islands, collapses with volumes of over 5,000 cubic kilometers, 1,200 cubic miles, have been identified. A number of such landslides have been identified in the Canary Islands, especially in the more active volcanoes El Hierro, La Palma and Tenerife, where about 14 such events are recorded through their deposits. They mostly take the form of debris flows with volumes of 50 to 200 cubic kilometers, 12 to 48 cubic miles, that emanate from an amphitheater-shaped depression on the volcanic island and come to rest on the seafloor at 3,000 to 4,000 meters, 9,800 to 13,100 feet depth. They do not appear to form through individual collapses. Multi-stage failures lasting hours or days appear to be more common, as has been inferred from the patterns of landslide-generated turbidite deposits in the Agadir Basin north of the Canary Islands. The most recent such event took place at El Hierro 15,000 years ago and was later redated to have occurred between 87,000 plus or minus 8,000, margin of uncertainty, and 39,000 plus or minus 13,000 years ago. Many processes are involved in the onset of volcano instability and the eventual failure of the edifice. Mechanisms that destabilize volcanic edifices to the point of collapse include inflation and deflation of magma chambers during the entry of new magma, intrusion of cryptodomes and dikes, and instability of slopes under loading from lava flows and oversteepened lava domes. Periodic collapses have been found at some volcanoes, such as at Agustin and Volcan de Colima. Shield volcanoes have different mechanical properties than stratovolcanoes, as well as flatter slopes, and undergo larger collapses than the latter. Finally, the mechanical stability both of the volcanic edifice and the underlying basement and the influence of climate and sea level changes play a role in volcano stability. Tsunami hazards. Large collapses on volcanoes have generated tsunamis, of which about 1% relates to volcanic collapse. Both small collapses and earthquake-linked landslides that took place in historical times generated tsunamis. The 1998 Papua New Guinea earthquake in particular drew attention to this hazard. The most recent such tsunami is the 2018 Sunda Strait tsunami, which was caused by a flank collapse of Anak Krakatau and caused at least 437 fatalities. The possibility of a large collapse of this volcano causing a tsunami was known already before the 2018 event. Other contemporaneous examples include the 1929 Grand Banks earthquake, the 1958 Lituya Bay tsunami, a 2002 tsunami at Stromboli that caused severe damage to coastal settlements, the 1888 tsunami caused by the Ritter Island collapse, which killed about 3,000 people and is the largest historical tsunami-forming collapse with a volume of 5 cubic kilometers, 1.2 cubic miles, and the 1792 Shimabara collapse of Unzen volcano in Japan, which claimed 4,000 or 14,538 victims. In total, volcanically generated tsunamis are responsible for about 20% of all fatalities related to volcanic eruptions. Prehistoric landslides that caused tsunamis include the Storegga slide 8,200 years ago, a 3,000 cubic kilometers, 720 cubic miles, submarine landslide off Norway that generated a tsunami recorded from geological evidence in the Faroe Islands, Norway and Scotland. The landslide has been modeled as a retrogressive failure that moved at a rate of 25 to 30 meters per second, 82 to 98 feet per second. Another landslide-induced tsunami inundated Santiago, Cape Verde, 73,000 years ago after a collapse of the neighboring Fogo volcano. More controversial is the evidence of past landslide-induced tsunamis at Kohala and Lanai in the Hawaiian Islands and at Gran Canaria in the Canary Islands, and other candidate deposits of landslide-induced tsunamis have been reported from Bermuda, Eleuthera, Mauritius, Rangoa and Stromboli. The size of such tsunamis depends both on the geological details of the landslide, such as its Froude number, and also on assumptions about the hydrodynamics of the model used to simulate tsunami generation. Thus they have a large margin of uncertainty. Generally, landslide-induced tsunamis decay more quickly with distance than earthquake-induced tsunamis, as the former, often having a dipole structure at the source, tend to spread out radially and has a shorter wavelength, while the latter disperses little as it propagates away perpendicularly to the source fault. Testing whether a given tsunami model is correct is complicated by the rarity of giant collapses. The term megatsunami has been defined by media and has no precise definition, although it is commonly taken to refer to tsunamis over 100 meters, 330 feet, high. Cumbre Vieja in the Atlantic Ocean. Cumbre Vieja volcano lies on the southern third of La Palma, Canary Islands, and rises about 2 kilometers, 1.2 miles, above sea level and 6 kilometers, 3.7 miles, above the seafloor. It is the fastest growing volcano in the archipelago and thus dangerous in terms of collapses and landslides. Several collapses took place since the Pliocene, followed by the growth of Cumbre Vieja during the last 125,000 years. The last eruption of La Palma was in 1971, the most recent subaerial eruption in the Canary Islands. During the Holocene, volcanic activity on Cumbre Vieja has become concentrated along a north-south axis, which may reflect an incipient detachment fault under the volcano. During the 1949 eruption, a 4 kilometers, 2.5 miles, long normal fault developed along the crest of Cumbre Vieja. It has been inactive since the prior eruptions did not form such faults, which do not have the appearance of graben faults. Geodesy has not identified ongoing movement of the flank. Unlike on Hawaii, flank movements at Canary Islands appear to occur mainly during volcanic episodes. Tsunamis are less common in the Atlantic Ocean than in the Pacific or the Indian Oceans, but they have been observed, e.g. after the 1755 Lisbon earthquake. Apart from fault lines, submarine volcanoes such as Kikum Geni and landslides are sources of tsunamis in the Atlantic. Tsunamis are not just known from the sea. The Viant Dam disaster in 1963 claimed 2,000 fatalities and was caused by lake-level tsunami, and evidence of past tsunamis is recorded from Lake Tahoe. Model by Ward and Day 2001. Ward and Day 2001 estimated that the unstable part of Cumbre Vieja would be at least 15 kilometers, 9.3 miles, wide in north-south direction. In light of the behavior of other documented sector collapses such as at Mount St. Helens, the headscarp of the unstable part of Cumbre Vieja is likely 2 to 3 kilometers, 1.2 to 1.9 miles, east from the 1949 fault, and the toe of the sector lies at 1 to 3 kilometers, 0.62 to 1.86 miles, depth below sea level. Bathymetric observations west of La Palma support this interpretation. They had not enough information with which to estimate the thickness of the block, but assumed that it would have a volume of about 150 to 500 cubic kilometers, 36 to 120 cubic miles, and the shape of a wedge, comparable to the Cumbre Nueva giant landslide 566,000 years ago also on La Palma. The authors used linear wave theory to estimate the tsunami induced by the simulated Cumbre Vieja. They used a scenario of a collapse of 500 cubic kilometers, 120 cubic miles, that moves at a rate of about 100 meters per second, 330 feet per second, on top of a layer of mud or landslide breccia, which lubricate its movement, and eventually spreads 60 kilometers, 37 miles, to cover a jug-shaped area of 3,500 square kilometers, 1,400 square miles. Ignoring that the landslide excavates part of the flank of Cumbre Vieja, thus assuming that it does not contribute to any tsunami generation, they estimated the following timing of the tsunami. 2 minutes. A 900 meters, 3,000 feet, thick dome of water rises above the landslide. 5 minutes. The dome collapses to a height of 500 meters, 1,600 feet, as it advances by 50 kilometers, 31 miles. Additionally, wave valleys form. 10 minutes. The landslide is now over. Waves reaching heights of 400 to 600 meters, 1,300 to 2,000 feet, hit the three western Canary Islands. 15 minutes 60 minutes, 50 to 100 meters, 160 to 330 feet, high waves hit Africa. A 500 kilometers, 310 miles, wide train of waves advances across the Atlantic. 3 to 6 hours. The waves hit South America and Newfoundland, reaching heights of 15 to 20 meters, 49 to 66 feet, and 10 meters, 33 feet, respectively. Spain and England are partially protected by La Palma, thus tsunami waves there only reach 5 to 7 meters, 16 to 23 feet. 9 hours. Waves 20 to 25 meters, 66 to 82 feet, approach Florida. They are not expected to grow farther as they hit the coast. France and the Iberian Peninsula would be affected as well. Further, the authors concluded that the size of the tsunami roughly scales with the product of the landslide speed and its volume. They suggested that traces of past such tsunamis may be found in the southeastern United States, on the continental shelf, in northeast Brazil, in the Bahamas, Western Africa. Later models. Mater 2001 employed a shallow water code that includes friction and the Coriolis force. Assuming shallow water behavior of the wave even with run-up, the eventual tsunami heights in the US and the Caribbean would not exceed 3 meters, 9.8 feet, and in Africa and Europe it would not be higher than 10 meters, 33 feet. Mater 2001 also estimated that dispersion along the US coast could reduce tsunami amplitude to less than 1 meter, 3 feet 3 in. Giesler, Weaver and Giddings 2006 used public domain bathymetric information in the so-called SAGE hydrocode to simulate the tsunami stemming from variously shaped landslides. The landslides generate a single wave that eventually detaches from the landslide as the latter slows down. The waves have shorter wavelengths and periods than teletsunamis and thus do not spread as effectively as the latter away from the source and decay away roughly with the inverse of the distance. Such tsunamis would be a greater danger to the Canary Islands, the eastern Lesser Antilles, Iberia, Morocco and northeastern South America than to North America where they would be only a few centimeters high. Loveholt, Peterson and Giesler in 2008 published another study that employed the worst-case landslide scenario of Ward and Day 2001, but used hydrodynamic modeling that accounts for dispersion, nonlinear effects and the deformation of the landslide material itself to simulate waves generated by such a collapse. In this model, the landslide had a volume of 375 cubic kilometers, 90 cubic miles, and a maximum speed of 190 meters per second, 620 feet per second. It generates a high leading wave that eventually separates from the landslide, while turbulent flow behind the slide generates lower waves. Overall, a complex wave field develops with a sickle-shaped front wave that is over 100 meters, 330 feet, high when it reaches a radius of 100 kilometers, 62 miles. The waves do not decay at a constant rate with distance, with the crestal wave decaying slightly faster than one distance while the trailing wave decays slightly more slowly. Thus, at distance the trailing waves can become higher than the leading wave, especially the waves propagating west display this behavior. Undulating bores also develop, a factor not commonly considered in tsunami models. In the Loveholt, Peterson and Giesler 2008 model, the impact in the Canary Islands would be quite severe, with the tsunami reaching heights of over 10 to 188 meters, 33 to 617 feet, threatening even inland valleys and towns and hitting the two largest cities of the islands, Santa Cruz and Las Palmas, badly. The impact in Florida would not be as severe as in the Ward and Day 2001 model by a factor of 2 to 3, but wave heights of several meters would still occur around the North Atlantic. Off the U.S. coast, wave amplitude would reach 9.6 meters, 31 feet. Abadi et al. 2009 simulated both the most realistic landslide geometry and the tsunamis that would result from it near its source. They concluded that most realistic volumes would be 38 to 68 cubic kilometers, 9.1 to 16.3 cubic miles, for a small collapse and 108 to 130 cubic kilometers, 26 to 31 cubic miles, for a large collapse. The initial height of the wave depends strongly on the viscosity of the landslide and can exceed 1.3 kilometers, 0.81 miles. Loveholt, Peterson and Glimsdahl 2010 noted that landslide-generated tsunamis can have a leading wave smaller than following waves, requiring a dispersive wave model. They simulated inundation in Cadiz resulting from a 375 cubic kilometers, 90 cubic miles, collapse at La Palma. The found run-up of about 20 meters, 66 feet, and the possible development of undulate bores. Abadi, Harris and Grilly 2011 employed three-dimensional simulations with the hydrodynamic simulator, Thetis, to reproduce the tsunamis induced by failures of 20 cubic kilometers, 4.8 cubic miles, 40 cubic kilometers, 9.6 cubic miles, 80 cubic kilometers, 19 cubic miles, and 450 cubic kilometers, 110 cubic miles. These volumes were taken from studies on the stability of La Palma's western flank, while the 450 cubic kilometers, 110 cubic miles, reflects worst-case scenarios from earlier tsunami studies at Cumbre Vieja. The landslide is directed southwestward and induces a wave train, with the 80 cubic kilometers, 19 cubic miles, collapse having a maximum wave height of 80 meters, 260 feet. At El Hierro, the tsunami can shoal and rise to a height of 100 meters, 330 feet, while the wave train surrounds La Palma and continues eastward with a height of 20 to 30 meters, 66 to 98 feet. Zhou et al. 2011 used numerical simulations to model various tsunamis, including a scenario resulting from a mass failure at La Palma. It assumes a smaller volume of 365 cubic kilometers, 88 cubic miles, as the collapse hits only the western flank and does not assume a southwest-directed propagation direction, thus increasing the hazard to the U.S. coast. The resulting tsunami approaches the U.S. coast between 6 to 8 hours after the collapse, in a north-to-south fashion. Waves grow due to shoaling as they approach the continental shelf but later decline due to increased bottom friction and eventually reach heights of 3 to 10 meters, 9.8 to 32.8 feet, when they come ashore. The impact of undulate bore formation on run-up is unclear. Abadi et al. 2012 simulated both the development of waves using dispersive models that include nonlinear effects, and the behavior of the landslide generating them through slope stability and material strength models. They considered both volumes of 38 to 68 cubic kilometers, 9.1 to 16.3 cubic miles, obtained from research on the stability of the flank of Cumbre Vieja, as well as volumes of 500 cubic kilometers, 120 cubic miles, as hypothesized by the original Ward and Day 2001 study. The slide has a complex acceleration behavior and most of the waves are formed during a short period early in the slide where the Froude number briefly exceeds 1. The initial wave can reach a height of 1.3 kilometers, 0.81 miles, minus 0.8 kilometers, 0.50 miles, and eventually wave trains are formed, which are diffracted around the southern tip of La Palma and go on to hit the other Canary Islands. With increasing volume of the slides, the wavelength becomes shorter and the amplitude higher, yielding steeper waves. Abadi et al. 2012 estimated a fast decay of the waves with distance but cautioned that since their model was not appropriate to use for simulating far-field wave propagation, the decay may be exaggerated. In the Canary Islands, inundation would reach a height of 290 meters, 950 feet on La Palma. Even for a 80 cubic kilometers, 19 cubic miles, slide would reach heights of 100 meters, 330 feet, in the city of Santa Cruz de La Palma, population 18,000, while the largest city of La Palma, Los Llanos de Aradane, population 20,000, may be spared. The waves would take approximately 1 hour to propagate through the archipelago, and important cities in the entire Canary Islands would be hit by substantial tsunamis irrespective of the landslide size. Taranarod et al. 2015 modeled the impact both of a worst-case 450 cubic kilometers, 110 cubic miles, landslide and of a more realistic 80 cubic kilometers, 19 cubic miles, collapse on Ocean City, Maryland, the surrounding area, Europe, Africa and the Canary Islands, using the Thetis and Funwave TD hydrodynamical models. They found that for a larger volume, the leading wave is both larger and forms farther away from the island. For a volume of 450 cubic kilometers, 110 cubic miles, the tsunami hits Africa after 1 to 2 hours, followed by Europe between 2 to 3 hours, the Central Atlantic between 4 to 5 hours and the U.S. continental shelf between 7 to 9 hours. At the continental shelf, the wave train slows down and the number of main waves changes. Bathymetry, such as the presence of submarine topography, alters the behavior of the wave. In the 450 cubic kilometers, 110 cubic miles, scenario, after slightly over 8 hours from collapse, tsunami waves reach the areas offshore the U.S. coast, where their height decays as they traverse the continental shelf. The eventual wave heights at the 5 meters, 16 feet, depth contour are about 0 to 2 meters, 0.0 to 6.6 feet. For the 80 cubic kilometers, 19 cubic miles, collapse in 1 to 5 meters, 3 feet 3 in minus 16 feet 5 in. For the 450 cubic kilometers, 110 cubic miles, collapse. Impact is worst in North Carolina, but also New York and Florida are impacted, even if refraction around the Hudson River Canyon mitigates the impact in New York City. In Europe, tsunami waves arrive after 1 to 2 hours, even with a smaller collapse of 80 cubic kilometers, 19 cubic miles. Impact around Coimbra and Lisbon is severe with waves of 5 meters, 16 feet, height, as Europe is closer to La Palma. Abadi et al. 2020 repeated their 2012 simulations using a model which incorporates viscous behavior to obtain wave heights in the Atlantic, the Caribbean Sea and Western Europe for landslides with a volume of 20 cubic kilometers, 4.8 cubic miles, 40 cubic kilometers, 9.6 cubic miles, and 80 cubic kilometers, 19 cubic miles. This simulation yields a lower initial wave height, 80 meters, 260 feet, for the 80 cubic kilometers, 19 cubic miles, landslide, and a flatter profile of the initial water level disturbance. Wave heights reach 0.15 meters, 5.9 in the Bay of Biscay, 0.75 meters, 2 feet 6 in, south of Portugal, 0.4 to 0.25 meters, 1 foot 3.7 in minus 9.8 in, along French coasts, 0.75 to 0.5 meters, 2 feet 6 in 1 ft 8 in, at Guadeloupe, all for the 80 cubic kilometers, 19 cubic miles case. Tsunami heights at Agadir, Açores and Sufi exceed 5 meters, 16 feet, at Lisbon, Coruña, Porto and Vigo about 2 meters, 6 feet 7 in, and along parts of the French coasts 1 meter, 3 feet 3 in Guadeloupe even a small landslide, 20 cubic kilometers, 4.8 cubic miles, can lead to widespread inundation. Ward and Day 2006 indicated that the combined effects of several wave trains may amplify the tsunami impact over that of a single wave. Research by Froelich et al. 2009 on boulders emplaced on Tongatapu endorsed the hypothesis of large landslide-induced tsunamis in Ramalha et al. 2015 identified evidence of a megatsunami, implying a single-step collapse, caused by the collapse of Fogo volcano in the Cape Verde Islands. Criticism. The findings of Ward and Day 2001 have gained considerable attention, amplified by increased concerns after the 2004 Indian Ocean earthquake about the hazards posed by tsunamis, and in turn increased awareness of megatsunami risks and phenomena. The coverage of the risk of a collapse gained criticism for exaggeration, in particular the coverage in North American and English media. They have triggered debate about their validity in the landslide and wave scenarios employed. Various models with different physical specifications have been used to simulate the waves induced by such a landslide. Later estimates have questioned the assumptions made by Ward and Day 2001, mainly with regards to the following. The authors employed a linear tsunami model that may not properly reflect nonlinear processes such as wave breaking that could reduce the height of the resulting tsunami by a factor of about 10. Wave dispersion might also act to reduce tsunami height since the wave induced by the Ward and Day 2001 landslide behaves as an intermediate water depth wave. The estimated speed and acceleration of the landslide may be unrealistically high for the slopes it would move on, and this inadequate to establish effective coupling between the tsunami and the landslide. Later research has found evidence that sufficient speeds have been reached during collapses at other volcanoes. The landslide modeled by Ward and Day 2001 may be implausibly thick given the known volumes of Canary Islands mega-landslides, and collapses may have occurred in multiple steps rather than a single failure or may have a smaller volume. The thickness of the landslide is a particular issue, as different estimates have been obtained at various volcanoes. Another issue is whether giant landslides occur as a single-step failure, as argued for Hawaiian giant landslides, or multi-stage failures, as appears to be more common in the Canary Islands, and stacking in turbidite deposits generated by landslides are a reliable indicator that these landslides occurred in piecemeal fashion. In general, many of these studies have found lower wave heights at distance than the original Ward and Day 2001 paper. There are also questions about the southern limit of the width of the unstable zone, about whether creep might stabilize it, and about whether it actually exists at all. Probability. Humanity has never witnessed enormous collapses on La Palma, and there is evidence that the western flank of La Palma is currently stable and a collapse in the near future unlikely. A worst-case scenario giant landslide like the one modeled by Ward in Day 2001 is a very low probability event, probably much less common than once per 100,000 years, which is the probable occurrence rate of large landslides in the Canary Islands. A smaller landslide scenario, which Taranarod et al. 2015 defined as extreme credible worst-case scenario, has a recurrence rate of about once every 100,000 years. Because of their low incidence probability, the hazard from large flank collapses at La Palma is considered to be low. Return periods are not the only factor involved in estimating risk, as the amount of damage done by an extreme event has to be considered. Globally, the return period of giant landslide-induced tsunamis may exceed 1 per 10,000 years. Potential impact. A Cumbre Vieja landslide tsunami may constitute a threat to Brazil, Canada, Caribbean, Ireland, Morocco, the northeastern United States, Portugal, and the United Kingdom. The impact would not be limited to humans. Aside from the tsunami hazard, the impact of a large collapse on people living on the island would be severe. The communities of El Paso, Fuencaliente, Los Llanos, and Tazacorte are located on the unstable block. Cumbre Vieja is largely unmonitored, and a flank collapse may begin with little forewarning. This item was read from the Wikipedia page, Cumbre Vieja Tsunami Hazard, as it was on September 15, 2021. Changes may have been made to the item since. Nice. You have made it to the end already. Thank you for watching. If you aren't already subscribed, please do so, as there will be more videos like this in the near future.